David, thank you first to invite us to make this presentation, to give us the opportunity to present our work. Thank you, Howard, to the time you took to help us in preparing the presentation. So all what we have done is public, is on this website, all the documents. The videos that you are going to see are already on the website, and the presentation today will be also on the website. There is no copyright, so the more what we do could be used, the better we feel. The team, I guess you had plenty of time to get on the internet to understand what are our CVs. To make it short, what's make our team specific is that we have some knowledge of air traffic control systems and procedures, and mainly their shortcomings. So why have we been doing that now for several years? And for this first reason, I don't know if we keep working on that until the wreck is discovered. Maybe. If the wreck is discovered, there will be still issues whether the black boxes could be retrieved, whether they could be readable, and even if they can read the voice recording system, the voice recording system is only for 2 hours. So maybe we never know all the answers. But at least we expect that if the wreck is seen in the end of the water, it will be a giant step for the families. The third reason, I always say that this story is interesting from the technical standpoint, but there are other dimensions which I would say I don't really understand, provided that I pretend that I understand even the technical side. The high level of safety of the air transport is the result of a systematic, what we call, return of experience. After each and any accident, there is a thorough analysis to understand what could have happened and to try to correct it. The Boeing 777, so far there are 2,000 orders. This is the flagship of Boeing. This is used by many airlines, Emirates, Air France. I don't understand why the French Aeronautical community does not care. And it's not just about the Boeing 777. I don't want to frighten you. Today, this is still possible to make an aircraft to disappear. So this is my first question, why the French Aeronautical Committee, including the official body, do not care about this event. In contrast, there are quite a few people who are interested in this disappearance. There are several categories. The first category are the conspiracy theories. There are quite a few. There are all which are coming back again. There are other which are popping every month. The last one is somebody has discovered from Google Maps that the aircraft is in the jungle of Cambodia, and the helicopter is going to find it. What makes all these conspiracy theories look alike, they do not care about any, let's say, plausible trajectory. An aircraft to fly from point A to B is not a bird, is not a rocket. There are some constraints. All this conspiracy theory, they do not care a dime about a trajectory. The second category, which overlap in a way, are those people who do not believe the data. We think that, especially two sets of data, the radar data and the Inmarsat data are being forged, are being manipulated. Us, that's not our position, because as engineers, if you do not trust the data, you cannot make any computation. But in a way, us, by our process as engineer, we are forced to believe the data which are available, and there is enough data in the reports to make the work that we have done. People think there is not enough data. There is a lot of data. Whether they have been forged, we'll come back on why the Malaysian air defense have been so slow to give the information, why the information is not complete, maybe some question about the Inmarsat data. The second question I have, and I do not know the answer, there are other data which are not necessary for work, but then I don't understand why some of the data as so far have not been made public. So that my second question, I have no answer to that. The third category is even more, I would say, strange. The Australian Transport Safety Board, who has been in charge of the search, we can come back on later on why it is the Australian, not the Malaysian, who have been put in charge of that. They made some assumption at a given time on the straight line going in the middle of nowhere in the ocean, in Indian Ocean. As a result of that, there has been two or three campaigns of search which have not been successful. And rather, like any scientific process, if the outcome is wrong, maybe you should reassess the assumption. Rather, to reassess the assumption, other people found explanations which are just after the fact explanation. For example, there's been hypoxia, that the pilot tried to commit suicide. There are a posteriori justification for something which is just an hypothesis. To make it clearer on the slide, here, we'll come back on the trajectory. This is the beginning of the trajectory, with strange change of heading. So obviously there was somebody in command. And then, all of a sudden, the Australian made the assumption that the aircraft went along that. As a result, as I said, there has been 3 underwater searches with equipment which is so efficient, and even the data have been displayed, they are public. If the wreck was there, it would have been found. So the wreck is not there. So why these people did not come back to a classical scientific process? Is there not another trajectory? And for me, this is the third question. I don't understand why these competent, intelligent people did not make what I consider a scientific process. So this is the reason why us, as a contrary, our hypothesis for a long while, this trajectory has been piloted from start to end for what piloting means. Nowadays, this is not the pilot which is moving the, okay? If you read carefully the so-called final report, you can read carefully, people could interpret this in a way or the other. For us, this is something which is supporting the work which has been done by Jean-Luc, Philippe Gasser. It has been 1 year of hard work, computing, simulation, under Michel and myself supervision, challenge, and at the end, this is what we are going to show you. A plausible trajectory as a result of an engineer work. Okay? And this is not an hypothesis that's been a suicide or something like that. It's the other round. It is from this plausible trajectory that we can make the assumption or support the fact that it's been an hijacking. And then will be the end of my introduction. Of course, it's very likely that in the question, some of you are going to ask us questions about the motives. At best, depending on the question, we may give you some clue. But we do not have the will nor the means to carry what is in fact should be a Secret Service investigation. And to end up my presentation, what has been done so far is a safety investigation, but there has been no security, that is to say, investigation, which should be the business of Secret Service. So this is my next question for which I have no answer. So again, during the question, you can ask a question on this 5 questions. For me, they are all surprise. I don't have the answer. So now I'm going to pass the buck, as the Americans say, to Jean-Luc, which is going to present an engineering work only.
The technical part of it, as Jean-Marc said, we're not going to see the why it has been done, but the how, and how we read and how we deducted or derived the trajectory. The first one is to say, okay, where do we start from? From the beginning, the report. What is written in a report, and we believe that the report has been done with serious work. So we started from that. We started also from the Inmarsat satellite data, and we'll see that a little bit later. We will see that, and I will not spend too much time on that now, but we have a set of information coming from Inmarsat, and we consider that it's a good basis to start from. We also used, and we spend a lot of time to review the community publications. They are a hell of a community, and especially the independent group, to which you should recognize their work and the benefit for the community, because they gave us a lot of models, they gave us a lot of indication, and they are still very proactive. And from that, we could use their models later on. We also used what has been later known as the recovered debris. You know that there are basically 30 identified debris, out of which 3 are sure to be from the aircraft. And this is providing information, and we use that also as the basis for the work. But also, the first issue when we discussed with Jean-Marc and Michel was to say, okay, there are trajectories, assumptions, but can the aircraft fly these trajectories? And actually, we set up a simulation environment to verify that indeed a Boeing 777 could fly such a trajectory. But also, coming from the operational background from the ATM, air traffic management and air traffic control, we have a different reading of the airspace. For us, the airspace is not just the sky. It's a set of blocks in which all the aircraft will fly in a certain organized way. And we have some experience. And this aircraft obviously followed these rules. So we'll see how. Of course, we use the aircraft, what is public. And what is public is the operational manual of the aircraft, and also any documentation you can find on the internet on the capacity of the aircraft. Voilà, and that helps us to derive a realistic operational trajectory using all these informations. And so to do what? But the first thing was to derive at each key point. We identified actually 24 key points, but 7 are official because they are the points where the satellites and the aircraft were in communication together. So deriving or deducing the trajectory, we could identify on those 7 points the values of these, let's say, modeled signal and compare with the original. And the comparison with that is offering us, if it's matching, a good match, and it's what it did. So the matching is validating the CAPTIO trajectory. So we will start now with a short video. So not now, I will explain what you'll see in the video. The video is very short, few minutes, but you will see different elements on that video, and so to understand it, you have to capture quickly what is going on. Well, basically, the aircraft is modelized, it's easy. Its trajectory is usually in red, And time to time you will see dotted line in front of the airplane indicating the intention. If it's in red, it's the normal flight plan that has been known by the ATM and ATC. If it's yellow, it's what we think the people on board were willing to do. Now you have different objects, like for example the routes, which are in purple, which are virtual routes that the aircraft are following. How? Because of few points which are marked, for example, in yellow here, which are all over the world. It's a grid. You don't see them. It's virtual points, but they have to follow points. And these points are routes, forms routes. Now, what is most important is that for the ATM point of view, you have zones in which states are responsible for controlling the traffic. For example, here you see that it's Bangkok, Thailand, is responsible of this area. When the aircraft is passing this boundary, it should change the controlling center of the controlling center. I will see that a little bit later. So the person in charge of the control of this aircraft here, it's not the same here, and likewise here and here. So you see Indonesian and so forth. Now, on top, you see that we have derived data from different set of data, and it's marked here. For example, this picture is from part 3 from the Inmarsat satellite data. Here you see the computed value of what we think was remaining as a fuel on board. It's a computed, just for the show. It's giving you the value that you have computed. Now here you see the shadow. It's giving you an indication of the flying level, the altitude at which the flight was at the time. And time to time, you see here tags appearing, which give you some of the key points we have identified where something important happened. And finally, you can see the progress of a timeline bar here. Now the video. Before we start our analysis, we made some hypotheses to reduce the number of potential solutions. We derived this hypothesis based on the observation of the first part of the trajectory, which shows a very well chosen location to reroute the aircraft, which shows clever maneuvers and a clear will to stay invisible as much as possible from the civilian controllers. So we assumed that there were people in command, but not only for this known part of the trajectory, but also until the end of the full flight. In addition, we consider that there was no damage to the aircraft and that these people in command aimed to land safely and respected the airspace structure and avoided as much as possible the radar coverage. Well, even though they let probably the flight management system of the aircraft to select the best and adequate flight modes, we think they could not reach their destination and probably they were forced to ditch somewhere before reaching their objective. Voilà. So for us, where does it started? Well, it's very important for us to show you that the location where the disappearance happened is very well chosen. And it's not by chance, not by coincidence. At the beginning, people were saying, oh, the aircraft got a damage, got an emergency. But when you look at the place when it happened, it's really, to our view, unlikely, and it's explained later on. So this zone is very particular. Few years earlier, you see that there is actually 3 zones of importance: Kuala Lumpur, Flight Information Region, Singapore, and Ho Chi Minh. You see that the aircraft was actually supposed to fly that way. That's its flight plan to Beijing. Right. So you see that here it has to cross this area. When an aircraft is passing a boundary between 2 fields, there is some process which is manual between the controller of that zone and this zone to carry over the aircraft. They are talking to each other by phone and agreeing how the aircraft will cross the boundary, right? So you see that here, normally, this aircraft here should have been negotiated between Singapore and Kuala Lumpur, and later on, Singapore to Ho Chi Minh, which means for a flight which is taking place for 10 minutes at most, the guys have in Singapore has twice the job for nothing, because in peacetime, there is no problem. It's an easy route. So there was an agreement to say, Kuala Lumpur, you are in charge of this zone in peacetime and to negotiate with Ho Chi Minh. So even though the transfer happened and was done in Igari, in people's mind to a certain extent, it's a zone where there is, let's say, no real issues, no real important difficulties. So that's why it gives us kind of a loose time to a certain extent. Now the aircraft arrived here, and what happened is that Igari, the traffic controller of Kuala Lumpur said, bye-bye, please do contact Ho Chi Minh Ville, because when an aircraft crosses a boundary, the pilot is responsible to contact the next one, right? And the next controller is basically in his state of mind waiting that the aircraft is calling him. And if not, well, basically he's waiting. And that's what happened at that time. So the aircraft arrived here, and Ho Chi Minh did not contact Ho Chi Minh, and Ho Chi Minh was just doing busy other stuff in the other part of the sector. And then suddenly, the aircraft disappeared. We know that the controller saw it disappeared, but in his mind, it's not an issue. It was out of his sector. He has transferred it, no problem. Ho Chi Minh took basically between, let's say, 17 to 19 minutes to react and to say, oh, by the way, where is the aircraft who should have called me? But he didn't call. So the aircraft has already 17 to 19 minutes ahead of the search. Because in aeronautics, in ATM, when an aircraft has not declared emergency, has not been identified in difficult situation, he is supposed to fly his flight plan. So the dot red line. So if a search will be triggered, it will be only there. So in that direction to Beijing. So it took basically the time that the people understood that the aircraft was lost. They didn't, let's say, follow properly the traces. It took them basically 4 hours to trigger, and actually 5 hours to trigger the research. So the aircraft was gone. Where was it? Well, taken the radar data that we've retrieved, and recently the recent civilian approach radar of Kota Baru here, the aircraft did a huge turn to come back, actually. And while people were busy searching here, actually the aircraft was already gone, long time ago, right? And how we will see that now. So you see now this is the latest, let's say, the important radar, military radar for Malaysia, which has captured spots of the aircraft. So now you know that this is the official route, and we know it's confirmed by air traffic control. That's a sure thing. Now this is the one that has been deduced by the radar data later on. What is important to note is that when the radar from the air traffic control, which was supposed to receive a response for the aircraft, there is an interrogation. The radar from the civilians are interrogating the aircraft, who is answering, saying, that's me, I'm flying at that altitude, that speed, that heading, and so forth. They didn't receive that. So what happened? Actually, manually, somebody took the control, because here we suppose that the power was cut off, but the power means electrical power. And then, manually, there was a huge turn. Why we know that? Because the shape of the turn is such that the aircraft cannot be automatic. It's manual. The banking angle is too strong, too large. So it's a manual turn. And then, after this turn, it's a clever way to come back, just on the top of the boundary of two fears, letting believe that, because here only military could see it, no more the civilian, basically. So then you let believe Bangkok that it's Singapore which is controlling the aircraft, and here that Kuala Lumpur is controlling, and the other one is believing the others is controlling. So it's kind of an Edgar Poe saying, I'm in the middle, but I let believe the others that I'm controlled by the other controller. So nobody reacted, as the aircraft calmly behaved and rejoined here this route. Now, in the middle, recently we discovered that here the aircraft was not at all descending because of an emergency. So the hypothesis of emergency damage or whatever is not confirmed, because actually the aircraft was accelerating and climbing. It's the contrary of what you do when you have an emergency. You want to go back to the first airport, but this one was probably closed. And the closest is either Penang, but probably also closed, as I understood, but probably also Kuala Lumpur would have been good, but not turning and going here. Now, what is very striking is that when the aircraft turned, a terrestrial antenna grasped a hook with a mobile phone of one of the pilots. There was no communication, no time to do anything, but it was recognized. It means the aircraft was in the vicinity here, which confirmed the radar track that has been followed so far. These points are given by the military radar, and what is interesting is that this is the last visible area for the military for Malaysia. Here, nothing is covered. And what happened is suddenly, out of it, the SATCOM is back. The SATCOM back means power to the SATCOM. And we will see later what it means. But we think that here the electrical power was switched back manually on, which means that from the beginning, the emergency is not proven at all, and in the contrary, it has been well piloted by somebody, and even like Edgar Poe, they used the normal route to go to Europe and to give the impression they were a traffic with just a communication problem. Right? Now, we talk about the satellite links. What does it mean? A ping. A ping is a connection between the satellite and the aircraft when the box, which is the modem, is establishing a communication or has an established communication with the satellite. And what happened here is because of the power which is switched back on, the aircraft or the SATCOM said to the satellite, I'm here, can we have a connection? Can we establish a link, a permanent link together? Now, the satellite is on a high geostationary situation over the Indian Ocean. It's not stable. It just moves a little bit around circle because that's a fact of life. You cannot be stabilized at that point. And the link is when we said the electronic power will be switched off, we thought about having people in the main equipment bay, which is beneath the cockpit. Here you can switch off fuses, switches, breakers, circuit breakers. But the SATCOM is here. So it's not switchable as easily as the other things. So when the power is back, then the people who did that could not know that this was again powered. And so they could not know, and this is driving the antenna, the steering of the antenna to the satellite, such that the link of communication is perfect, basically. So let's continue to that. There is a communication between the satellite and the aircraft. There are two things to measure, and that can be measured. Since the accident of the Rio-Paris, the Air France flight, Inmarsat has installed pieces of software in their communication where they measure two things, a time and a frequency. And this gives us the distance to the aircraft to the satellite, and the other one is the Doppler, right? Now, this is given us when we receive or when the satellites receive such information, then we can deduct by the distance to the aircraft satellite, we can identify the circle. So the aircraft at that time when it's received is on the circle, which is intersection of two spheres, one centered on the satellite and the globe, the Earth globe, at the altitude of the aircraft. And the Doppler is actually the change of frequency because of the movement of the aircraft and the satellite along this axis. Right, it's too much. I will stop there for the technical stuff. Now, what is beautiful is that to sustain and to avoid overlapping of communication, frequency shift, and to ensure that the channels are well centered between the aircraft and the satellite, the aircraft is carrying on board a software which is adjusting automatically at any time the frequency of the signal is sent to the satellite. It corrects that with the horizontal speed, its heading, and the satellite ephemeris, but it doesn't compensate for the vertical speed of the aircraft. The software ignores that component. Because of that, the compensation is not perfect. And thanks to that, we've got the BFO. Otherwise, we would just have got the BTOs. And so that's an information which is of very much of interest. So now, what do we got from that? We got actually a set of circles. Of course, these circles are supposed at a certain altitude. If you change altitude, it's not a pile of circles, it's a sphere. So you see, they are moving. But nevertheless, and why do we get these circles? Because each time there is a link, the satellite is saying, you're a nice guy, but you're costing me a lot of resources, and I'm keeping for you a line open. Are you still alive for me to keep it open? Otherwise, I close it and I give it to another aircraft. right? So every hour or so, there is a watchdog trigger, and the satellite is saying to the aircraft, hey guys, are you here? And every hour, the aircraft or so has answered. It's not exactly every hour, and I will explain you why. So we've got a set of 7 circles where the aircraft could be around the globe. Now, how can we reduce that? First, looking at the signal frequencies and stuff like that, people have determined that the north is not possible. And second, the range of the aircraft, it cannot be on the other part of the globe, remains the southeast quarter that you see here, which is the most logical and which has basically been confirmed later on because we found debris which arrived at La Réunion. Right, now on top of these 7 measures, we have actually 2 sets of measures of very good interest. 2 phone calls from ATC. The phone calls went via the satellite, but they were not answered. So the first one here actually reset the trigger. That's why we didn't get 1 hour exactly between the first and the second arc, much more because they placed a call. And because they placed a call, it reset the trigger. Luckily, they didn't spend their life to call the aircraft. So that's why we've got so many, let's say, sparse arcs. And as we are concerned, we never used these arcs for computation of our trajectory, but we use it as a confirmation to confirm whether our computations were okay. Right. Now, radar coverage, it's another aspect. When you look at that, you say, how could today an aircraft not be seen with such a huge, massive radar coverage? That's true, but now it's a question of perspective and responsibilities. Right, let's come back to the basics. You see here the area, and you see the numerous zones of traffic controls. Each of them is actually split in sectors under the responsibility of one man. Right. For those people who have radars in the vicinity, they don't care at the time of the flight. Why? They were not in charge of Kuala Lumpur. And the aircraft made everything possible to stay within Kuala Lumpur. So for them, no reason to worry. This aircraft is in Kuala Lumpur. Why should I bother to check an aircraft which is under the control of the other one? In addition, it never showed any threat to the people. No orthogonal flight to Indonesia, which are very sensitive. No Thailand, they were just on the boundary. And it used a route going to Europe and India. So why to bother? These people didn't care. And they were not. And the military even more didn't care. They were not threatening. So even there was some coverage, the aircraft behaved relatively normally, let's say, in the Malaysian airspace, but nevertheless, the question is, that's true, the military in Malaysia should have seen the way back. That's a question. Now, the next one is Thailand, but Thailand has no reason. They were well within, but no reason to bother. The same for Nicobar, and the same for Indonesian. So now the question is, and that should be of very much interest, can we retrieve these data? Do they have some record? Because if they have, I'm sure we will see something happening here, and they must have. Now, what is interesting for us is that here, you see in that radars, I showed you some military mainly, because for the civilian, the aircraft was invisible. It didn't react to the secondary radar, so it was not visible, only the primary. Now, for this, at this part, that's the boundary of the secondary radar, where normally the aircraft should have responded. But it took the care to turn around and to avoid to be within a zone where it was supposed to answer the questions. As I said, the military should have. And later on, and that's why I show that, the Australian radars, because we'll be concerned about that, have got different radar on the way, and we will see that a little bit later, and also a famous detection system for boats, but also low-flying aircraft. And that's the trajectory we found. Flying relatively normally here, we'll see what happens here, but basically avoiding the radar at the boundary again with Kuala Lumpur and Chennai to change level directions. And again, when it entered Indonesia, and the same when it entered Australian area, to finish close to Christmas Island, where we thought it would land safely. Right, now coming back, this is for the airmen a Michelin cart, a Michelin map. It's when you take your car, you use now a GPS, but this is a chart showing the routes. This is what now you know well, the route of the aircraft. Having here something we will look precisely in a moment, and then a final turn. Why and what happened at this time? Well, if you look at this chart, there are a lot of routes coming from Europe, going to Europe, to Dubai, and these routes have what we call minimum flight level. We are convinced, and actually the data has also helped us to be convinced, that these people respected the rules and went under the route to pass, or above the route, under, and descended to avoid traffic and to respect, for two reasons. One, because they wanted to fly safely. Second, is to show the military who could survey them that they were respecting the rules. So no worry and no specific attention to them. Now, I will show you a very quick video where what we've done in this video is we have, you know that today when somebody of your family is flying, you can follow the flight real time by Flying Aware, Flight Radar 24 or Plane Finder. We've used a mixture of this information to reconstruct what could have been the traffic at this time of that day and why the aircraft would have done what we call a contingency procedure. So you have to be careful. In this video, the yellow are those who are given by these softwares I mentioned. When they are in green, it's what we have reconstructed. And when they are in black is the aircraft, the MH370, being, let's say, vanished, disappear from the screen, but still flying in this vicinity. And there are two aircraft of interest, and I will help you to identify these. So here is accelerated traffic. You will see, we will not spend too much time. Here is the MH370, which is lost by surveillance radar. You know that around the globe, people have got receivers, traffic management controllers, and they get data broadcasted by the aircraft. And here is an aircraft of interest, Emirates 343. And this Emirates is going to Dubai. And here appears an Indian coming from Madras, from Chennai, which is Indigo. Here it's at the flight level 340, 330, and this aircraft is supposed to be at also 330, 340. To avoid to cross these aircrafts, it had to go to a contingency procedure, offset and then descent to pass underneath. So what is of interest, and here you will see appearing the ID card of the Indigo. So at the time where the aircraft was there were actually two aircraft. And actually a witness said that she had seen at least two aircraft and another aircraft which was in an orange glow around the aircraft. But it means that there were traffic at that time. If you look at the profile, what happened, it's actually the aircraft climbed normally, the hijacking took place, he flew in cruise, and then it had to pass under the route, which are the bars. And because of that, it entered a mode which is an economic descent, which has a particularity to keep the aircraft at a constant indicated airspeed of 240 knots, which is very important because actually it looks constant, but actually it's not. The further you go down, the slower you fly because the air is denser, so you don't need to fly faster. And this is constant evolution of the speed, which lead to a final flat end of cruise at a pseudo, let's say, constant, because here you have the FMS of the computer of the aircraft, which is optimizing the fuel consumption. Now, we said safe landing. Now, looking at safe landing, because we knew from reading the trajectory, they were looking for a safe place. There is no suicidal, there is no damage. So we said, where could they land? There are different places. The most important are Jakarta, Christmas Island, Learmonth, and Cocos Island. Now, considering what the fuel was on board and the capacity of the aircraft, we said the flyable distance, Learmonth is impossible. We did several simulations. We never arrived in Learmonth, and our simulator is optimistic. We were always short of fuel and falling in the water. Now, if you look at what was the flight plan originally, the aircraft was supposed to fly from Kuala Lumpur to Beijing, which is 2,500 kilometers. It's interesting to note that going to Christmas that way is basically the same distance, nautical miles, I said, not kilometers. And it's 100 and something kilometers, 140, which with a reserve of fuels is not normally an issue. The issue is that at low profile, it consumes much more fuel. And that's what I'm showing here. Normally, a flight is supposed to climb, be flat, and descend, and use some fuel, and the computation is there. And if something happens here, it has a reserve. Being there, there is a clear overconsumption. And that's why they, for us, were short of fuel. So what we did is, using our simulators and the document available, we looked at the community with their fine and nice models which compute, let's say, the fuel. We did that every second of the fuel. And the interesting element is to show that with the scientific community models, on the Arc 7, we just are short of fuel. Well, the model is not that precise. Nevertheless, we found that it's zero fuel, which, let's say, not demonstrate, but give an additional argument that actually, yes, the flight finished because they were not having enough fuel. They were exhausting the complete fuel. Now, the debris. You heard about the debris. So this is an old map. Since then, there were some others, but it gave a good indication of what happened. This is the location, so you will have the presentation later on, so you will have a look. But basically, this is the aircraft and the different debris that have been found at different places here. What is for sure is that there are 3 debris which have been certified, identified as coming from the aircraft. The others, there are still some questions and need some confirmation. Nevertheless, it's interesting to see that these have appeared on this coast of La Réunion and Tanzania and Maurice. We'll come back later on that. Now, what we've done, the community told us, yes, your trajectory is nice, but what about the debris? We said, okay, let's have a look to the debris. So we spent some time to do the modeling of the debris, and we selected the most important one, which is the flap, the flaperon. The flaperon is just above the engine and cannot expand as the others because the flux of the thrust of the engine. And so in the water, the flaperon is half immerged, or let's say partially immerged. And a part of it is subject to the wind, while another part to the current. So we use the CIRO model, Australian Research Establishment, to see whether we could do an equivalent. Here is the result of the study, and actually I will show you very quickly the video. Voilà. So our hypothesis and the difference between the other studies is that we used real meteorological data. Philippe, our guru, fetched the data, and we used this data to simulate from our expecting end of flight 121 points for which we calculated the path and their estimation time of arrival. And this is justifying the fact that the debris, can I see it? Yes, that the debris have arrived properly at La Réunion on time. And now, as a recall, the search were made so far there, as Jean-Marc mentioned, and the endpoint that we have identified is much further north. The very important element in the last report of the Malaysian is that the French organization in Bretagne and then in the south of Paris made an analysis of the barnacles, the shells attached to the flaperon, and they showed actually that they are coming from very high temperature waters. And these waters are only in this area up front. Here, it's cold water. So that's also explain why this trajectory is possible. Well, I will skip that one. And finally, this is the recall of the trajectory. And what we think is that they didn't know that the right engine was consuming 150 kilo, that's our computation, more than the left engine. And because of that, they are lacking the ton of fuel that they would have allowed them to land to Christmas. Let me summarize that our findings. We found a plausible piloted trajectory from start to the end, fully compatible with the Inmarsat data or the other data like the airspace structure, for example, and so forth. We found that this trajectory is indeed confirming that the fuel was exhausted and it finished via or by a ditching probably at the end. Because of the low altitude at the end of the flight, the aircraft could not glide so much around. Thus, the search zone that we have identified on the southeast of Christmas is relatively small compared to the search zone that have been searched so far. Now, what will be the future? For CAPTIO, the first step will be to challenge the trajectory with a professional simulator, for example, a training simulator. That will be the first step to achieve. The second one will be to find or to convince authorities and to find sponsorship for searching in this small zone. Because of this size, we estimate that the cost will be much lower than the cost faced so far in the previous searches. And this is the end of the presentation, and the CAPTIO team, thank you very much for your listening. And we thank also the Royal Aeronautical Society and especially the Paris Branch for hosting this event. Thank you. Goodbye.